purpose of today's lesson is to allow you to actually draw out these orbital notations. And as we learn how to draw out the orbital notations, we'll also be reminding ourselves how the information from the orbital notation relates to the quantum numbers that are required in our description of the quantum mechanical or electron cloud model of the atom. So we're going to start with this example that I've drawn out here. We have 1s, 2s, 2p, 3s, 3p, and we have these arrows above those. If we count the total number of arrows, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, that tells us the number of electrons in our model. Assuming that we're looking at a neutral atom, the number of electrons would also equal the number of protons, which means we can now identify the element of our atom based on the number of arrows we have. So if we have 14 electrons and we're assuming it's neutral, that would be 14 protons, which means if we look that up on the periodic table, we're actually representing silicon. We also can look at each piece of our orbital notation, the 1s, the 2s, the 3s. These numbers are representations of a principal quantum number. And if you remember back to our last video, the principal quantum number, that relates to the size of the energy level. So in this example, we would say that there are 1, 2, 3 energy levels occupied. That just tells us that if our nucleus is here, we have a total of 3 sized regions that we're looking at. The next thing we have are these letters, S's and P's. The S's and P's, the letters, those represent our angular momentum quantum numbers. And those letters, with the numbers that they're combined with, tell us the shape of each subshell. So within each of these energy levels, these sized regions, we have specific shapes. Some regions only have one type of shape, like the first energy level only has a sphere. But the second energy level has both S and P. So that would be our sphere, this guy here, and some regions that are figure 8s. They're really just two-lobed regions. Now, with the P, we also have these lines. And the lines represent our magnetic quantum number. And the magnetic quantum number tells us the orientation of some of the regions around the X, Y, and Z axes. So in the P regions, these subshells, we have 3 different orbitals. Each line is an orbital. 1, 2, 3, X, Y, Z. So we could draw that same sized shape on both the X, the Y, and the Z axes, and that would be 3 different orbitals, but all 3 of those orbitals are within the same subshell because they're the same size and shape. And then, of course, we also have the up arrow versus the down arrow, which is our spin quantum number, which for right now, we're just going to consider the spin of the electron around its own center. So if it's an up arrow, we'll say it's going clockwise, and if it's a down arrow, we're going counterclockwise. The reality is a little bit more complicated for that, but for right now, that's a good enough understanding. So one thing that we could do is look at an orbital notation that's already drawn out and identify the information for a specific electron. For instance, this electron that I colored in red, we could say is above the second energy level, so we know that that's 2 rings out from the nucleus. 1, 2. We could say that it's in a P subshell, which means it has to be some sort of figure 8. And because it's on the 3rd line, that's on the Z-axis. So specifically, we know that that electron is most likely traveling somewhere within this region that's on our Z-axis. And we also know that because it's pointing down, it's spinning counterclockwise on its own center as it travels somewhere within that region. The other thing we can do is actually count each type of region. So if we're looking at energy levels, we could say that since the biggest number we have is a 3, silicon's electrons occupy 3 energy levels. We could then count the number letter combinations, 1, 2, 3, 4, 5, and we could say that silicon's electrons occupy 5 subshells. We can count the lines that have at least one arrow above them. So that's 1, 2, 3, 4, 5, 6, 7, 8. And we could say that there are 8 orbitals. Those are our lines that the magnetic quantum number describes. And we could also even say that there is one orbital that is not occupied. It's an empty line. And we could point out that there are 2 arrows that are unpaired, meaning there's an up without a down, and a total of 4 electrons in the outer energy level, which eventually we're going to call those valence electrons. There's a lot of information that you can get from an orbital notation that's drawn out for you. And that's one of the goals today, is to continue practicing that. But the other goal for today is really to allow you to be able to write these orbital notations. And in order to do that, there's really 2 things that you need to get in your brain. The first is the number of lines that go over top of each type of subshell. And that's a pretty easy pattern to remember. S's have 1 lines, P's have 3, D's have 5, and if we continue the pattern, 1, 3, 5, F's would have 7 different lines. And just remember, each line represents the possibility of rotating the orbital to a different location around an axis. We remember the lines for the P just because it's easy, X, Y, Z, but the D and the F are similar, except they're not along the axis directly. They're kind of rotated, so you'll get things like x squared minus y squared, or x plus y, or x plus z, just different locations within. The other thing that you're going to need to remember is the order of the subshells. So 1s, 2s, 2p, 3s, 3p, and you could just memorize that. You could look at what we call the diagonal rule, which is written out in your textbook if you like that version. Your textbook has the entire thing, but basically it's just you list out all of the subshells and then you draw diagonal arrows, which will then tell you the order that these get filled in. So 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p. There's another version though that is actually the one that we're going to spend just a little bit of time today listening to. And I'm going to go through this version with you just because it really does help later on if you have an analogy to kind of think of some of these things being like. So we're going to spend a little bit of time today in story time. And the story that I'm about to tell you is called The Electron Boarding House. Now, the first thing that I need to point out to you is that this is really just a story. It is not real. There is not really a crazy landlord that tells electrons where they have to sleep within their boarding house. This is just a story, an analogy to really help you get your brain around what some of these concepts are like. So we do have a crazy landlord in our electron boarding house. He gets to make the rules, and we don't get to question the rules. So for today, I really just need you to kind of relax, watch the electron boarding house as the blueprint comes kind of to life, and just try to learn the rules. Not so much question them, just try to remember what those rules are. So if we begin our story, we have a house. And within our house, it's a boarding house, which means that we have lots and lots of rooms where people can pay pretty small amounts of money in order to just kind of stay for the night. It's not like a hotel, there aren't any great amenities, but it is a cheap, clean place to sleep. Now, unfortunately, our electron boarding house is run by a pretty crazy landlord. And he's so crazy that nobody can really question what he does. They just have to follow his rules. Now, the first thing that our crazy landlord does is number his boarding house kind of backwards. So if we think about like this being street level and you walk in on the bottom floor, a lot of times that would be the ground floor or the first floor. But our crazy landlord, he's decided that he wants to number his boarding house from the top down. So when the first person comes in to stay at the boarding house, the landlord decides he's going to open up a room all the way at the tip top. And this first room that he opens all the way at the tip top is a pretty small room. There's really only one set of bunk beds, which means 2 total beds, a top bunk and a bottom bunk within that room. And because it's over on this side of the building, where the sun is at for the majority of the day, he decides to call this the 1S room. First floor, it's all the way at the top, sunny room. So the first person comes in, the landlord opens up the first floor sunny room, and when he opens the door, he sees that there is exactly one set of bunk beds in that room, which means the first person to come in, he says, you need to go to the top bunk. And then the second person comes in and he says, okay, you're going to be on the bottom bunk. And that room is now filled because you can't have more than one person on a bunk bed. So when the third person comes in, the landlord has to open up another room. And the next room that he decides to open up is still on the sunny side of the building. But because now it's beneath it, it's on his second floor, he's going to call this the 2S room. Now, all the rooms on this side of the building are pretty small. They really only have one set of bunk beds, which means they can really only hold 2 people. So the first person in, that's person number 3 total, he says, you take the top bunk, and person number 4, you take the bottom bunk. And then the landlord goes back to his office. When the 5th person comes in, the landlord decides he wants to open up a slightly bigger room. He doesn't want to have to keep running up and down this flight of steps every time, so he goes to the opposite side of his building. And he actually opens up this room right here. Now you might notice it's a little bit bigger. Instead of just having one set of bunk beds, this room actually has a total of 1, 2, 3 sets of bunk beds, which means it can actually hold a total of 6 people. And because 6 people will eventually be in that room, it gets a little crazy. The rooms on this side of the building, we're going to call the party rooms because they're just bigger, they can hold more people, so that's where the party's at. Now it is on the second floor, you might notice. It wasn't all the way at the top of the building. So he's going to enable this, the second floor party room, that's 2P. And he's got a really, really crazy rule. When people start filling into this, he decides to actually assign all the top bunks before any of the bottom bunks get filled in. So person 5 in the boarding house goes to a top bunk, as does person 6 and 7, but person 8, 9, and 10 all go on the bottom. Room is filled, he has to open up another one. So we're going to come back over to this side. Now by now you might be able to predict that because this is on the left side of the building, that's the sunny side, and it's the 1, 2, 3rd floor down. This one's going to be called the 3S. Sunny rooms always have one set of bunk beds, which means person 11 and 12 can fit in there. After 3S, he comes back over here again, opens up another party room. This one's on the 3rd floor, so that's 3P. Party rooms always have 1, 2, 3 sets of bunk beds. So that'll fit person 13, 14, 15, 16, 17, and 18 before he comes back over again and opens up 4S. 19, 20. After 4S is open up, his house has a total of 20 people residing within it. So it's getting a little crazy, it's getting a little loud, and really our landlord is just trying to keep things a little bit more calm. Unfortunately, when you have 20 people in one house, that's kind of a hard thing to do. But our landlord, in all of his wisdom, decides there is a way that he can solve his problem. And that method is actually going to rely on a different type of room. You'll notice that this is on the 4th floor. However, there's a lot more spots available. This has a total of 1, 2, 3, 4, 5 sets of bunk beds, which might make you think, well, that's even going to be worse. There's going to be a lot of people in there. But this center set is actually set up in such a way that it immediately makes anybody who goes in that room pretty scared. And the reason is this center room is actually a dungeon. So we had our sunny rooms over here. We had our party rooms over here. And then when the house just got too loud and crazy, we opened up the dungeon. Now, you might think, okay, 4th floor dungeon, but really when you think a little bit harder, where are dungeons always found out? Where's your dungeon found out? It's weird if you answered that question, by the way, but yeah, dungeons are usually found in basements. So one thing you're gonna have to remember about our boarding house is that even though this is the 4th floor, this is actually considered the 3rd dungeon. The way that I remember it is the sunny rooms were the first type and they started with 1. The party rooms were the 2nd type and they started with 2. The dungeons are the 3rd type of room and they're gonna start with 3, even though they're on the 4th floor. Now, because it's a dungeon, everybody in the house is going to get pretty quiet. Even these people over in the party rooms realize he has dungeons available. They're going to be pretty quiet as well. So we can actually fit in person number 21, 22, 23, 24, 25, 26, 27, 28, 29, and 30 in our dungeon. And at that point, people are quiet enough that he's willing to open up another party room. So we're back to the 4P. 1, 2, 3, which means we can hold person 31, 32, 33, 34, 35, and 36. (37) and 38 are over here. That would be our 5S. Then we have our 4D, 5 lines over top the D. And then we have 5P. And at this point, you might be saying, okay, I get it. There's a story. There's the sunny room, the party room, the dungeon. I understand that we've got numbers and letters, so S's start with 1, P's start with 2, D's start with 3. But I don't understand how this is going to help me remember the order of our subshells. Usually about now, though, somebody in the class will realize that this picture that I'm drawing, it's not just a blueprint for the Electron boarding house. This picture I'm drawing is actually our periodic table. And the fact that the picture is our periodic table, just with one slight adjustment, helium gets moved over to the sunny room. That's the power of the story, and that's why it allows you to figure out the order that our subshells are filled. So imagine taking your periodic table, moving helium over here. Now elements 1 and 2 are over on this side. Well, which side of the boarding house was that? That was our sunny side. So we can start by numbering our periodic table. With the sunny sides, and sunnies go from 1 all the way down to 7. So that takes care of number 1, 2, 3, 4. They're all in sunny rooms. But electron number 5 goes where element number 5 is, and that's over here on the right side of the periodic table. So on this side of the periodic table, we're going to not label our party rooms. But party rooms start with 2 instead of 1. So this is 2P, 3P, 4P, 5P, 6P, and 7P. And then in the middle, between what we would call our S block and our P block, we have the transition metals, which are known as our D block. Now remember, sunny rooms started with the number 1, party rooms start with the number 2, dungeons, they start with the number 3. So this would be 3D, 4D, 5D, and 6D. And then eventually, tomorrow when we work on some more complicated orbital notations, you're even going to use these down here. Now these would be our F block, and F's get, remember, 7 lines. That's a total of 14 elements across. Sunny rooms start with 1, party rooms start with 2, dungeons start with 3, and these F blocks, the flower rooms, would start with 4. So that's 4F and 5F. 1S through 7S, 2P through 7P, 3D through 6D, 4F, and 5F. If you can number your periodic table like this, that's going to help you determine the order that our subshells fill in, because all you have to do now is follow the atomic numbers. So we're going to do one more example together. Let's pick something that has, let's go with germanium. That's 32 electrons. If I want to draw the orbital notation for germanium, I need 32 arrows. I'm not going to put all 32 arrows in this 4P room, because if you look at germanium, there's only 2 arrows in that room. That means the other 30 arrows have to go in rooms before 4P. In order to draw your orbital notation using your periodic table, all you have to do is follow the atomic numbers. So start with 1. Where are 1 and 2 at? Well, that's the 1s. So I would start by writing 1s. S's always get 1 line, and that's 2 arrows. Then I go back to the periodic table and say, where are 3 and 4 at? Well, 3 and 4 are down here in 2s. So again, that's an S, so that's 1 line. There's 3 and 4. 5, 6, 7, 8, 9, and 10 are in 2P. P's get 3 lines. And remember, the crazy rule is that all the ups have to go in first, and then all the downs. So even though 5, 6, and 7 are next to each other here, we don't go up, down, up, down, up, down. We actually would go up, 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 down, down, down. 11 and 12 are here in 3S. 13 through 18 are in 3P. Up, 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 down, down, down. 4S has number 19 and 20. 3D gets the next 10 arrows. And then we have 4P, but we only need 1, 2 more arrows in order to get to our element. We're still going to draw all 3 lines for the 4P, but then we're just going to put in the first 2 up arrows. Now, if we count our total number of electrons at this point, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 31, 32, it has to equal our atomic number. And that's how we know that this is the correct orbital notation. We followed the rooms that filled into the periodic table. We put the correct number of arrows above each room, and we always put 1 line above an S, 3 lines above a P, 5 lines above a D, and then when we get to it tomorrow, we'll also be putting 7 lines above the F. And after we have these drawn, now we can count the different types of regions that are found within it. So if I want to count energy levels are like the floors of the boarding house. So I can say, well, we've got things on the first floor, we've got things on the second floor, we've got things on the third floor, and we've got things on the 4th floor. So there are a total of 4 floors occupied, so that's 4 energy levels. Subshells are like the rooms of the house. So I can count those. 1, 2, 3, 4, 5, 6, 7, 8. Orbitals are like the lines. Those are the bunk beds, the sets of bunk beds. One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. I wouldn't count the last one because it's not occupied. And then when we get to it, we can also count unpaired electrons. That's up without a down, so there would be 2 of those. and something called valence electrons, which are any electrons above the biggest number. So since 4 was our biggest number, we would count a total of 1, 2, 3, 4, what we'll call valence electrons. Now the last thing that we need to talk about today, once again, are just the rules of the house. And those are really the rules that we need to follow anytime that we are writing an orbital notation. And there are 3 rules that we actually talked about. You just need to know the real name of them. So the first rule, again, is the off-bow principle. And the off-bow principle is the one that tells us the order of the subshells. It really just states that subshells have to fill in from the lowest energy to the highest energy. Now that doesn't necessarily mean lowest energy level to highest energy level. It usually does, but occasionally you'll have a 3 that comes after a 4, and that's just because that orbital, or those types of orbitals, those subshells, really require just a little bit more energy than the ones before them. So if you follow your periodic table blueprint, 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, 5d, 4f, 6p, 7s, 6d, 5f, 7p, then you're going to know the off-bow principle, because it just says that you have to fill in one room before you jump to the next. The next rule, that was pretty obvious, is the weird one. It's the Hund's rule. And sometimes I just call that the up, up, up rule. What it actually says is that orbitals of equal energy, so basically the orbitals within the same subshell, have to be singly occupied before any of them gets doubly occupied. So you have to have one arrow on each line before any line can have the second arrow. Up, up, up before down, down, down. And that occurs in any P, D, up, 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 down, 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 or when we get to it, even the F. Anytime you have more than one line above the same room, you have to fill in all the ups before you fill in the downs, and they have to be facing the same direction. So you can't go up, up, down. That would still break Hund's rule, even though they each only have one arrow. All 3 of those lone pairs, or the unpaired electrons, have to be the same direction. The third one is really the one that would look the weirdest if we broke it. And it's probably something that you would not do automatically. Pauli exclusion principle just states you can't have 2 electrons within the same atom that have the exact same set of quantum numbers, which really just means you can't have 2 arrows that face up on the same line, or you can't have 2 arrows that face down on the same line. You'll have plenty of examples where electrons have 3 of the 4 quantum numbers the same, but the last quantum number, whichever one it happens to be, principle, angular momentum, magnetic spin, one of those 4 has to be different. You can't have 2 arrows on the same line that face the same way. And those are the 3 rules that we also need to follow anytime we're writing our orbital notations. And at this point, you're actually going to get some practice drawing out some of the simpler ones by yourself. You'll check those answers, and then tomorrow we'll talk about the more complicated ones.